Okay, so let's look at Chapter 2, the atomic theory of matter. If we look at the variety around us, we know diamonds are transparent, salt is brittle, nitroglycerin is explosive. These are all macroscopic observations that we can tell by looking at them. But to understand these things, we have to look at the microscopic level. All right, so let's say I take a piece of aluminum foil, all aluminum, and I tear it in half. Is that the smallest piece of aluminum that I can possibly have? Of course not. Do I ever get to a smallest? If I keep tearing and tearing and tearing and tearing, will I ever get to a smallest piece? Well, the answer is yes. It used to be that scientists thought centuries ago that you could keep going infinitely, but no, you do get to the smallest piece. Of course, I physically can't do it, but eventually, if you could keep tearing down, 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 you would get to the atom. The atom is the smallest particle of an element that still retains the properties and characteristics of that element. Okay, so that's important. It's the smallest particle that retains the properties of that element. If I take the atom and I break it down any further, then of course I don't have aluminum anymore. I have protons, neutrons, and electrons. So an atom is the smallest particle that still retains the properties and characteristics of an element. All right, so let's talk a little bit about how the atomic theory was discovered is not the exact word, but was developed. So the very first person on record to have talked about the atomic theory was Democritus back in BC 760 to 370. He was the first to argue that there was a limit to the divisibility of matter, that you eventually got to a point where you could stop. That it wasn't infinitely divisible. However, most people laughed at him, and that kind of never got off the ground. So it wasn't really until 1803 when John Dalton proposed his atomic theory that it became part of modern chemistry. So John Dalton. So John Dalton basically said all matter is composed of indivisible particles called atoms. All atoms of a given element are identical. Atoms of different elements are different from each other and have different properties. We form compounds when atoms of more than one element combine. Just to drill a little bit more, a compound is a type of matter composed of atoms of two or more elements chemically combined in fixed proportions. We talked about that in the last chapter. And then atoms of elements are not changed into different types of atoms. They are only rearranged, recombined. So this was actually quite a new idea at the time. So when we Okay, so an atomic symbol is what we use to indicate the different elements. It's a one or two letter notation used to represent an atom. It's important that the atomic symbol consists of a capitalized first letter. Often it comes from the name of that element. There's generally an additional letter, which would be lowercase. So there's only 26 letters, but there are 118 elements, so we need to use a combination. A lot of times they come from the name, so O for oxygen, N for nitrogen, C for carbon, but a lot of them may not make sense at first till you think about some of where they were derived from. So for example, silver with Ag comes from the Latin argentum, and Au for gold comes also from Latin aura. And so you can see how they're connected. copper, Cu, is from cupric, from Latin again. W for tungsten actually comes from German for wolfram. So a lot of different ones. The symbols are listed in table 2.1 in your book, and of course on your periodic table. The video that's on this slide is just a fun little video that's names all the elements. All right, so of course we know today that Dalton wasn't exactly right, because we know that we can break an atom down into smaller particles. And so some other scientists, we're going to look at what they did and how they discovered some of the different parts of the atom. So scientists at the beginning of the 20th century, the 1900s, knew that there was a nucleus, that there was a central core to the atom, and that it was positively charged, and that it contained most of the atom's weight. And then we also know that there are electrons that are negatively charged and are in the outside region of an atom. So how did that come about? Well, in 1897, the British physicist J.J. Thomson was the first to determine that there was something smaller than an atom. And he shot a cathode ray, which is just a stream of charged particles, and it came out of, he heated up a lamp, and these cathode ray particles came out of the lamp, shot these particles from the cathode to the anode. Here's a picture of the cathode ray. You can see that it's high voltage, and so there's a gas in there, and or a metal or something like that, and so it's a negative charged ray that's coming out of the cathode tube, and we know it's negative because you can see it's being attracted to the positive pole of a plate. The picture below, of course, is just a real cathode ray, which is the precursor to the television. They developed the television from cathode rays. So there you can see that if you grab it with the positive electrode, it will be attracted to it. If you put the negative end of a magnet to the other to it, it'll go the other way. So it is a negatively charged particle. So Thomson's experiment determined that atoms are divisible into smaller particles. We know that one of the subatomic particle is negatively charged, and so it was assumed that there had to also be positively charged particles to make the balance. It didn't matter which substance was used. It was always a negative particle that came off of it, so that indicated that the same negative particle is in all substances, and so these particles were called electrons. So Thomson was able to calculate the charge of the electron's mass to its, or the ratio of the mass to charge to mass ratio, but he didn't know the actual charge of the electron. That would come later. And like I said, he knew there must be positive charges. He didn't know how they were arranged, so he had what was called the plum pudding model, which looks sort of like this. He had negative and positive ions just all mixed up inside the atom. So he's called the plum pudding model. In 1909, another scientist, Robert Milken, performed his oil drop experiment. He took oil and dropped it through an instrument that had charged plates, positive and negative. If he turned the charged plates on, the electrons were attracted back up to the positive plate, and so actually he could stop these oil drops from happening, and he was able to measure the rate of the dropping oil with without the electric plates, and then with it on, he was able to stop them and slow them down and everything. Anyway, he was the one who discovered determined the absolute charge of an electron. So the charge, you don't need to know this number, but it's 1.602 times 10 minus 19 coulombs. And the mass of an electron then was determined to be 9.1 times 10 to the minus 31 kilograms. So very, very tiny. Here's just a picture of his oil drop experiment. And if you're more interested, you can look at this YouTube video that describes what's happening. Now, Ernest Rutherford was a student of J.J. Thomson, and he designed an experiment where he shot alpha particles. Alpha particles are particles that are positive 2 charge. He shot them at a sheet of gold foil and then measured around the foil to see where those particles ended up after they were shot at the gold foil. Now, alpha particles are much, much smaller than gold atoms, and so he didn't know how they would interact. So what happens is the alpha particles come out of that radioactive source, and they come through and they hit that gold foil. Now, again, if you want to see a little bit more, the YouTube video is worth watching. But mainly, we'll see on the next slide what happened. He didn't know what to expect. They might all come through, or they might all be blocked, or what. So he actually, what he found was that most of the particles went straight through. So that indicated to him that most of the atom is empty space. Some of the particles were deflected, indicated that they came close to something positive and got bent away from it. And a few particles came straight back, indicating that they hit something solid. So this little picture shows a little bit of what he's saying. So you can see most of the alpha particles come straight through. So most of the atom is empty space. A few of these alpha particles came close to the nucleus, which was positive, and so they got deflected away. So that's the scattering. They were scattered away. Some of them actually came almost straight back, which indicated that the positive charge was really dense. And that it was only in one small part of the atom. So some of them passed straight through, some of them were deflected slightly, and some of them were scattered quite a bit. So anyway, from his research, he came up with the structure that there was a positive nucleus in the center of the atom, and that the electrons and the negative charges were in mostly empty space around the center. It turns out that if the atom is, the diameter of the atom is about 100,000 times larger than the diameter of a nucleus. So the nucleus is very tiny and very dense. So we still don't know the understanding of how electrons are organized, and that we will put off till another chapter. But this is how we've just determined that there was a nucleus, protons, and electrons. This little link here is a simulation, which is kind of fun to play with, where you can actually scatter alpha particles and see what happens. All right, so again, the modern picture of the atom continues to be more detailed, but there's things like quarks and I don't know what all else. That's kind of the realm of physicists. But as chemists, we sort of take a simple view of an atom. So like I said, in a future chapter, chapter 7, we'll learn more about how the electrons are structured within the atom. But for right now, what we want to know is that the nucleus is in the center and it's dense. It's made up of 2 particles, the protons and the neutrons, that just about the most of the mass of the atom are in the nucleus, and that most of the rest of the atom is empty space, and that the protons, being positive, are in the nucleus. So the proton is a nuclear particle, has a positive charge. It's the same charge but positive of the electron. The electron's negative, the proton's positive. They're the same charge amount. But that the proton weighs about 1,800 times bigger than an electron. The number of protons in the nucleus is what determines what the element is, and it's referred to as the atomic number, and it's given the symbol Z. Z for atomic number. I don't know why they didn't just give it A for atomic number, but they used Z. All right, so an element whose atoms all have the same atomic number is different from another element whose atoms will have a different atomic number. So every element has its own atomic number, and if you're looking at the periodic table, it will be the whole number, usually at the top of the periodic table, sometimes at the bottom, usually at the top. I think, let's see, on the periodic table in your book, it is at the very top center. So that's the whole number. That's the atomic number, and it's the number of protons. So a neutron is also, like I said, in the center of an atom. A neutron is pretty much identical in size to a proton, but it has no electrical charge. So notice the chart below summarizes the particles. You don't need to know the absolute mass or the absolute charge by heart. You can see that the charge of the proton is the same as the charge of an electron, but opposite charge. The neutron's charge is 0. You can also see that the proton and neutron are about the same size in mass, but an electron is almost 2,000 times smaller. But I do want you to know that the relative mass, which is proton and neutron are 1, and electron is about 0 in 3 significant figures, so close to 0, and that the charge of an electron is -1, the charge of a proton is +1, and the charge of a neutron is 0. All right, now there is such a thing as isotopes. So first let's talk about mass number. So we noticed from the previous slide that protons and neutrons have about the same mass, and that that electrons are pretty much 0. So all the mass of an atom come from the protons and the neutrons. So the mass number is the total of the number of protons and neutrons in a nucleus. It is related to the other number on the periodic table, but that is not the exact same number. So a mass number should always be a whole number because it is a total of individual numbers of protons and neutrons. A nuclide is an atom that has a particular atomic number and a particular mass number. So we can write nuclides in a shorthand method, and what we do is we put the symbol for the element, and then the atomic number is a subscript to the left of that element. Here we can see sodium. Sodium has 11 protons, so 11 is the atomic number. It's the subscript to the left of sodium, and then the mass number, which is the total number of protons plus neutrons, is the top number to the left. So sodium 23 is a sodium atom that has 11 protons and 12 neutrons. You find how many neutrons by subtracting the bottom number from the top number. So this has 11 protons, 12 neutrons, and a total mass number of 23. And that's how we write, this is called a nuclide symbol. So we can actually have different elements and remember, elements that are the same, any element that is the same has to have the same number of protons, but the neutrons can differ. So in fact, if two elements have the same number of protons but a different number of neutrons, they're called isotopes. Isotopes of each other have the same atomic number but different mass numbers, and that's because they have a different number of neutrons. So chlorine, for example, there are 2 isotopes of chlorine that are stable, chlorine 35 and chlorine 37. So we can write the nuclide symbols like this. Since both chlorines have 17 protons, the bottom number is the same, but the top number is different because we have different number of neutrons. So chlorine 35 has 18 neutrons, and chlorine 37 has 20 neutrons, so it has 2 more neutrons, and these are called isotopes of each other. And again, notice that if you look on the periodic table, chlorine has a number 35.45, which is not either of these numbers. So remember, a mass number is a whole number because it's equal to the protons and the neutrons, and we're talking about a single atom when we write a symbol like this. All right, so how many protons and neutrons do we each have? 17 protons, 18 neutrons for chlorine 35, and 20 neutrons for chlorine 30. Okay, so most elements occur in nature as a mixture of isotopes. So lots of different elements have. So carbon, for example, has 3 different isotopes. Carbon 12, carbon 13, and carbon 14. Oxygen has 3 isotopes. Chlorine, like I just showed you, has 2 isotopes. Now, the number that's on the periodic table, which is not a whole number, is the average atomic mass of all the isotopes that exist in nature. Now, it's not a straight shot average So for example, carbon, there's a carbon 12, a carbon 13, and a carbon 14. So if we thought, well, the average of 12, 13, 14 is 13, but you can see that on the periodic table, the number is 12.01. That's because it's a weighted average, and it depends on the fractional or relative abundance of each isotope. So it turns out that for carbon, 99% of all carbon is carbon 12, and so that's why the average is closer to 99. We'll talk about that on the next slide. So here's another example. Boron has two naturally forming isotopes, boron 10 and boron 11. Now, just by looking at the periodic table, we can see that the average 10.81 is closer to 11 than it is to 10, so we can just if nothing else, we can say, oh, there must be more boron 11 than boron 10 because the weighted average is closer to boron 11. And in fact, if you look on this chart here, we can see that about 80% of all boron is boron 11 and about 20% is boron 10. This little link here that you see on this slide, PFET Colorado, is a really interesting isotope. It's just it's a simulation that you can play with, and you can look at different isotope masses. I believe I have a link on Blackboard that's a worksheet where you can work through this PFET simulation and answer some questions. And it's not anything to turn in, but if you want a little more help with this or a little more experience playing around with isotopes, that's a really good place to look. And like I said, there's a worksheet on Blackboard that has a link to this as well. All right, so to get a weighted average, what you do is you multiply the mass times the fractional abundance and then add them together. If you use the percentages, you can multiply the mass times the percent, add them together, and then at the end you have to divide by 100 because you're using percent. So either take the percent and convert it to a fractional abundance, or divide by 100 at the end. So again, a weighted average takes into account how much of each isotope is present. So in this case, because the 10.81 is because there's more boron 11 than there is 10, the average is closer to 11 than it is to 10. Just for your information, another example of a weighted average would be your class grade. So in the class, exams are worth 45% or 50%, depending on if it's taken online or what, but labs are only worth 15%. So we know that exams count 3 times as much as the labs do. So that means they're weighted more. Now, what do you expect if you have one bad lab? You don't expect it to affect your grade as badly as one bad test will, because your test, your grade, your average at the end should be closer to your test average than it will be to your lab grade average. All right, so let's actually do a calculation. So there are 3 isotopes for magnesium, magnesium 24, 25, and 26. There's the exact mass because the protons aren't exactly 1 and neutrons aren't exactly 1. So the mass of magnesium 24 is 23.985. The mass of magnesium 25 is 24.986, etc. The abundance is in the third column. So you can see almost 79% of magnesium is magnesium 24. So even before we do the calculation, we expect our average to be closer to 24 than it is to 25 or 26. About 10% is magnesium 25 and about 11% is magnesium 26. So what we do is take the mass times the abundance, add them all together, and then you get your weighted average. So the atomic weight of magnesium is 24. And again, don't get this mixed up, 24.305. That's your average. If you see just a whole number, that will be the isotope. Now, these abundances are not something you can know. You have to be told or look them up or something like that. So if you were given a problem like this, you would be given all this information and you would have to calculate it like I did here.